two further talks before lunch, and the first one is given by Mike Nieves on interaction of in-plane waves with a structured penetrable line defect in an elastic lattice.
Thanks very much, Malte. So thanks also to the organisers, Anastasia and Gennady, for giving me this opportunity to speak on my joint work with Prasant Sharma from IIT Kanpur. So I'll just dive straight into the problem. What I'm going to consider is an elastic lattice, a triangular elastic lattice formed from a triangular periodic distribution of point masses. And inside this lattice, there is a line defect. So these grey nodes at the junctions have a mass m, and they're interconnected by elastic rods that deform axially. And somewhere in this lattice is a defect that has masses with a mass capital M, so different from those in the ambient medium. And the motion of this system is completely in plane. And what we're going to do is look at a scattering problem where we send in a in-plane wave and look at how this interacts with the defect. So what will come up, what we'll do is we'll take our total field, which represents the displacements of the nodes, and here M1 and M2 are indices that locate the positions of nodes, which you count via the bottom lines in this system. It's written as an incident field, where you'll notice the time harmonic factor e to the minus I omega t suppressed. Here, plus a scattered field, so this is the amplitude of the scattered field. And we're going to write the problem for the scattered field and show how this can be reduced to a Wiener-Hopf equation along the line of the defected row. Okay, right. So if I don't have time, this is what happens in the lattice. Let me just see if colours look better. No, it's just the colour scale. It looks terrible on this screen. So at low frequencies, maybe you can see this, I don't know. At low frequencies, this is looking at the scattered field, so total displacement for the scattered field. This arrow is just indicating our incident wave is having this incident angle for this computation. What you'll see is you get some reflection from the defect, this inertial defect, of course, as you'd expect. At certain frequencies, what you have are defect modes, and Sasha spoke a bit about this earlier. And these defect modes correspond to vibrations that propagate along the defect, and which can help in enhancing transmission of the incident wave in the region below. Maybe, maybe not. You can also see there are circular wave fronts, or maybe you can just imagine that they're there. And this is sort of what you would probably expect to see in the classical analogous continuum model for this. Now, what's different about the lattice is when you go to higher frequencies, well, you have periodicity in the structure, and this periodicity brings you dynamic anisotropy. And what then tends to happen is you start to get effects such as, negative refraction, which we all know about now in the field of metamaterials, and also negative reflection as well, where a portion of energy can be reflected back into the quadrant where this incident wave is coming from. And you'll see, you can't see any circular, outward circular propagating waves from the tip of the defect. Now, so what we are actually going to employ is the so-called discrete scattering theory, which you can find in papers going back to 2015, but which was initiated by Prasant Sharma, and who studied the discrete analog of the Sommerfeld problem. So you have a crack in a square cell lattice, and so this crack is represented, a semi-infinite crack represented by an absence of links between two rows. You send in an incident wave and you want to know how this scatters. And it's reduced to a Wiener-Hopf equation through the Z transform to along the line of the crack. You can extend this technique and look at different defects, different lattices. So it's been done for instance, hexagonal lattices and lattices which have say defects which are rigidly fixed. You can also extend this technique to look at, say, how waves propagate along carbon nanotubes, which are partially unzipped, so there's a defect there. Or look at how cracks in lattices scatter Rayleigh waves at the tip. More recently, so this was all related to scattering by one-dimensional defects in structured materials. More recently, and there was a talk earlier this week by Andrei Korolkov on this. There is the paper by Andrei Shainin and Andrei Korolkov who look at scattering by a two-dimensional domain in a lattice, which also uses Wiener-Hopf. Now, what I also think is it's good to point out, and Sasha also highlighted this before, is there's a connection with this analysis. There's some overlap in the techniques being used to study these problems with the problems looked at by Leonid Slepian in the dynamic fracture of structured materials. Okay, slightly different mathematical problem, and also different physical phenomena there. Here the defects are static, there the defects are moving with a certain velocity. Right, so this is the problem now I'm going to try to formulate. So we have to look at nodes inside the bulk of the lattice and nodes situated along the defect, and write down the governing equations using Newton's second law. Okay, so we're doing this for the scattered field. And to do this, well, I take an elementary cell, I look at the node in the center, and then I try to write the equation for that node just by balancing the elastic forces with the inertia term. But to do this, I have to use these lattice basis vectors that help me to project the forces produced by the links on the x1 and x2 directions. Okay, now, so for this node in the center of this hexagon, which is contained in the bulk, you can write down the equations in this form. You have an inertia term, and they're your elastic restoring force terms. What to say here? I've employed a normalization where we've normalized with respect to the ambient lattice parameters, so that we're going to put the emphasis on what the defect will do in our problem. So this, you'll see in the next slide, gives us a contrast parameter, which allows us to see how this affects the scattering process. Oh yeah, final thing, and this was spoken about quite a bit during the week and earlier this morning by Sasha. There's some, this is omega hat, there's some small dissipation in here added onto the incident wave frequency, and this allows us to build a physically acceptable solution to the problem. Okay, and more about that later. So along the defect, you're doing the same thing for the scattered field, and here you have to take into account that actually your inertia varies if depending on where you look at along the row containing the defect. And this leads to a discontinuity in the inertia terms in the equations, which you can represent, or you can combine the equations governing those masses along that row using the Heaviside function. Now, in this is a contrast parameter beta that results from our normalization, and beta simply relates the mass from the nodes, the mass of the nodes outside the defect, to the mass of the nodes along the defect. So in this case, if you look at this expression, if beta is greater than 0, masses along the defect are heavier than those outside. We call this a heavy defect. And for a similar reason, when beta is less than 0 and greater than -1, we have a light defect. Now, I haven't said anything about this yet. Incident field, we have to construct this as a solution to an eigenvalue problem. And this field satisfies the equations external to the defect. Now, it doesn't satisfy the equations along the defect. And this brings in this forcing term in your equations both there. Okay. Now, moving on, more about the incident wave. take that solution, plug it into your governing equations for the nodes outside the defect. You would like this incident wave to satisfy those equations. And this gives you a homogeneous system. You have this coefficient matrix depending on the frequency omega and the incident wave vector. Okay? And then to build a non-trivial vectorial amplitude for the incident wave, you have to look at the degeneracies of this system. And this leads to dispersion surfaces for your material. And because of the periodicity, you have a finite pass band, and this corresponds to this frequency range. This is the frequency range we'll be interested in, because this is the one where you can send the incident wave in to interact with the defect. So at low frequency, what you see are these are slowness contours, if you're not familiar with them. How do you get these? Take your incident wave frequency, take a horizontal plane equal to that frequency, and what you get from the plane when it intersects these surfaces are these contours. And they help us to define our incident wave vector wave numbers. At low frequencies, they look like circles, and you've got two surfaces here. So in the low frequency regime, you're looking at shear, pressure waves, etc. in the medium. At higher frequencies, you've got this anisotropy, and so now you start to get things like this, ellipses. And in this case, what happens is you have dynamic anisotropy, and waves like to propagate in only certain directions in the system. Okay, so to define that incident wave, just take a point on the contour of your choice, and then you can build your incident wave vector as a solution of this eigenvalue problem. Okay, so now coming down to the stuff with Wiener-Hopf. We take the Z transform with respect to the x1 coordinate in the lattice, or with respect to the horizontal coordinate for the nodal positions. Looks like this. When we get to the Wiener-Hopf equation, we use the additive split that just naturally appears due to the discontinuity in inertia terms. If you apply this transform in the bulk, so outside the defected row, you get a series of relations like this. These are actually recurrence relations in M2. With coefficients independent of N2, and these things are easy to solve. Then, if you do this along the defected row, then of course you start to pick up the half transforms, because we had Heaviside function to represent the contribution of the inertial defect. And you have a transform of your load corresponding to that incident wave that appears in those equations. Now, we're going to solve these first, and then come back to this. So, how to solve these? Well, equations in the bulk. You look for your solutions in this form. C and D are vector amplitudes we have to find from another homogeneous system, written like this. Lots of details suppressed. But these systems, you have these matrices as degenerate when lambda here satisfies this condition. Now, what I wanted to mention, I forgot, we want to have a solution that doesn't grow at infinity when in our lattice. So we look at the case where modulus of lambda is less than 1. And you can build this lambda you have two of them as a solution of this biquadratic that satisfies this condition. Okay, so if you have two of these, then your solution in the bulk is a linear combination of two solutions of this type. You do this, and what you then do is you project that solution onto the line of the defect, and you find out that the displacements along the row N2 are related to the displacements along the line containing the defect in this way. Now, what's important is coming up are these matrices, coefficient matrices. They give you some symmetry properties in the modes, and we'll see this in a bit. Okay, then, so we'll press on. Okay, so that's your bug solution. You plug that into your now transformed Wiener-Hopf equation, and you work a bit, and eventually what you find is you have this Wiener-Hopf equation along the defected row. Okay, and so this here Z's a parameter that runs around the unit circle, and a complex variable that runs around the unit circle in the complex plane. What was surprising, but maybe not given the symmetries of modes that we'll look at later, and probably the geometrical symmetry, is the fact that after all of this, it's in fact your kernel function in the equation is diagonal. And okay. So this means you've got two scalar Wiener-Hopf equations, and we all know how to approach these and solve them. Now, in terms of the physics, you've got this kernel function. Zeros tell you about localized defect modes that propagate along this inertial defect behind the tip. And we've got singular points inside these kernel inside these two functions, and they give you the sort of wave radiation into the bulk due to the interaction of the incident wave with the defect. And those modes decay like 1 over square root r, as you'd expect, away from the defect tip, with the oscillatory factor on top. Okay. So that's supposed to say in the complex plane. So what happens? So we had some dissipation added to the frequency. And so suppose we don't put that dissipation in, then all the zeros and poles corresponding to real waves in the medium lie on the unit circle in the complex plane. As soon as you add this in, they get relocated, okay? And they shift from this C, this unit circle in the complex plane. And where they shift, Raphael mentioned the other day, is dependent on the group velocity associated with those wave modes. Okay, so this is by no means an accurate picture, but it's giving you an idea of we have branch points inside and simple zeros of the kernel function inside and outside. Now we'll come back to this in a bit, because what happens is only some of them contribute to the physics in the actual solution. Okay. Now I'm skipping the solution part to the Wiener-Hopf equation, but it's standard to solve these two scalar Wiener-Hopf equations that we have, and you get that your U0F along the defect is written in this way. Now, you've got your L minus, the inverse of, oh, by the way, we're using the Cauchy formula to factorize L, this matrix L, and you've got the inverse of the factor L minus, and you've got L plus. So the zeros of L minus, which correspond to the localized defect modes, give you some contribution to your inverse transform, which is going to come in a bit. You've got these singular branch points of L plus, which are going to tell you about modes outside the defect. And not to forget, you add the load in your equation. Once this is transformed, this gives you additional simple poles that lie outside this annulus. Okay, so a picture of this is coming up. Oh, and one more thing, that's the solution in the bulk. We'll remember this in a second. Yeah, so I've briefly spoke about this. I've faded out those singular points that don't contribute to the actual physics of the solution in the far field. Okay, so you have to worry about simple poles, simple zeros of L minus, and you have to worry about the simple poles corresponding to the incident wave, and then these branch points inside here. Okay. That's when you do the inversion of the Z transform. So this is how it looks like. Now I've got this structure inside the kernel, P and Q, are these matrices that we see in the bulk solution. There's actually a nice structure to all of this. These are actually related, I'll show you in a second. And UF0, well, I'll tell you a bit more about this, what is happening near its singular points. So, in fact, what happens is for a majority of its singular points, U0F it behaves like some singular function f multiplied by 1, 0 or 0, 1. Okay, just happens that way. And P and Q are related in this way. The off-diagonal components of Q are the same magnitude but opposite sign to the ones in P. And what does all this mean? Well, if you have a scenario like this, if you're near a singular point and you have this kind of representation, where you have 1, 0 here, you're going to pick off the first column of P and Q. And this gives you some interesting information about the symmetry of that particular mode. It means, if you look at the top formula, that you have this scenario. U1 is an even, U1 horizontal displacements of the masses are even functions with respect to the line of the defect, and U2 are odd functions. In the other scenario, where you have 0, 1, you have the opposite scenario. U1 is now an odd function with respect to the line of the defect, and U2 is an even function. Okay, and we like to call these tensile modes. In that case, think of mode 1 fracture. When you're pulling the crack apart, you get a similar sort of response like this. And when you have mode 2 fracture, you get a field that satisfies this. Okay, so you'll see S and T appearing a bit more in a second. So just to hammer this home, yeah, so I'm going to put the emphasis on the defect modes, and they correspond to simple poles, say Z0 of your UF0. Okay, so you have this asymptotic representation to leading order near that pole, and D is a vector that's proportional to 1, 0 or 0, 1. If you then compute its contribution through your inverse transform, you get a defect mode like this. Heaviside function who gives the support of this mode behind the defect tip. So these are just modes. This coefficient S is P and Q multiplied by D. So when you have D, which is 1, 0, the defect is in this sort of tensile mode. Yeah, so it's compressed, or it's in a sort of compressional or extensional mode, and you have this type of response where it's highly localized in the vertical direction towards the line of the defect. When you have a case which is 0, 1, you won't be able to see it from here, but this thing is snaking the wave along the defect. It's we call it a transverse vibration mode, and it's of the type S. Okay, they're probably better names, but okay, moving on. Right, now, singular points of L, you can trace these in the complex plane as you increase the frequency. And what happens is you get something like this that looks like spaghetti running wild on a plate. And probably if you're from the metamaterials community, you like to look at those things there. And you can, if you just make this connection, and then everything unfolds out into the omega K plane. Your choice what you want to do. They're curves for the bulk. I'm not going to have time to go into those. But we essentially perform this procedure, trace all branch points and poles. We understand what the dispersion curves are for the defect. So we have dispersion curves for longitudinal defect modes and transverse defect modes. You can trace the bandwidth. You can see how the bands interact with the bands for the bulk. And you can have things like disjoint dispersion curves, i.e. dispersion curves defined for the defect on disjoint intervals of the wave number. Okay, so tracing the width of those bands for the defect modes, you can come up with a band diagram like this, which is omega against beta. I'm almost done in a second. So Information you glean from this is, well, probably as expected, the light defect likes to vibrate at higher frequencies. And in particular, if you have a regime where you have a transverse mode, it's always accompanied by a longitudinal mode. So this is the band for the transverse mode. If you have a heavy defect, you can have a different scenario. There is a region where you can have both transverse and longitudinal modes that propagate along the defect, or you can have them appearing separately, depending on the frequency. In the intermediate region, you've got this funny state where a heavy defect likes to only support longitudinal modes, and a light defect likes to support transverse modes. Okay, this is COMSOL computation. I'm going to be quick now. You can try with damping, etc., with lots of effort and time to get the sort of solution to your scattering problem. I ran out of steam, and you get, in this computation, still some imperfections from the borders, okay? But anyway, it's good enough to make a comparison with the solution I showed you before. And yeah, so this is based on the inversion of the Z transform and solution to the Wiener-Hopf problem. This is the COMSOL computation I showed you before. Again, isotropic response, it's consistent with what you have in the bulk, i.e. these circular wavefronts that propagate from the tip. And if you want, you can look at a total field. Right. I think I'm going to finish in 2 seconds, maybe more. At higher frequencies, you get dynamic anisotropy starting to creep in. So in this case, you have like a contour that's a hexagon with rounded corners. And then you start to see things like preferential directionality of waves that emanate from the tip. Hopefully you can see. Yeah. Last case, interestingly, at high frequencies, when you have these ellipses, you start to get wavefronts that have this sort of, that propagate outwardly like this from the tip. It's an ellipse, which is oblique. You get negative refraction and amongst other effects. And I think that's a good time for me to stop. So we've extended the theory now to look at in-plane vector problems, but there's plenty more to do. Thank you.
Thank you very much, Mike. It was a very nice talk.
You showed one Riemann-Hilbert problem, again, a Wiener-Hopf problem, with coefficient that is a rational function, and you use, as understood, Cauchy integral. It's of course a matter of taste. I mean, but the question is probably where you had the representation of the kernel that was one. Oh yeah. But looking at this function instead of a function of z, I see that the degree of polynomials on top and bottom not the same. So it means that
lambda should apply. Lambda also.
Index, but it should be some kind of
it is.
Constant.
Yeah.
All over.
Absolutely.
That Cauchy integral can be evaluated.
Yeah. Yeah. So yeah, this has been checked. Lambda also depends on the complex variable z. So there's asymptotics
but yeah,
and behavior of lambda to consider.
Have you got any non-uniqueness or some? Why? But the index is not zero, but there should be this balance.
The index is 0.
Why it is not 0? It's 0.
But the degree of polynomial is different.
No,
Lambda
but
also
lambda
depends
depends on z.
So how does lambda go at the large z?
Oh, I can't remember, but we can take a look after.
Ah, yes, that's true.
Yeah, but lambda plays a role in this.
Yeah, you're right.
Yeah. So.
There is z squared, yes.
Yes, but lambda depends on that as well. So then
Yeah.
Huh?
lambda 1 and lambda 2.
Lambda is a function of z.
Ah,
Lambda, yeah, I can't say, yeah. But it's fine, yeah. So all those computations also we checked that index is 0, but lambda does play a role in the in this.
So it makes sense, man.
Maybe, I don't know. Right.
You hide the important.
Well, it's too much to fit on the slides, I think.
Can I ask about the incident wave?
Yeah.
So obviously, not every incident wave is allowed.
Yeah.
And so does it mean that at certain frequencies, which are not very small, some directions are excluded? What do you do about it?
So
for example,
direction.
you have the diagram.
Yeah.
Below. Yes.
The direction's determined by K1 and K2.
So you always pick the permissible ones, don't you?
Yeah, that's right.
The other thing is, you mentioned on one of the slides tensile mode and shear mode.
Yeah.
And of course, for the isotropic continuum, that's absolutely fine. But for the lattice, I don't think you can do it because again,
Well,
in the long wave approximation, that's fine. As soon as you go up, you can introduce the notion of lattice flux and lattice circulation.
Okay.
Pressure and shear waves you can think of as curl-free or
Yeah,
divergence free.
because it's a bit delicate, isn't it, at
but-
higher
but-
frequencies to find them.
But
Yeah.
for the lattice, as soon as you go to higher frequencies, they're all coupled in general. So you can't really identify tensile or
No, you can, well, okay, go on.
in the sense as I have described. So you compute lattice flux and lattice circulation.
Yeah, but as maybe I'm misunderstanding. As I mentioned, these singular points in the kernel give you information about certain modes that you might see in the far field,
Alright.
and then each individual mode it has this symmetry property, and maybe tensile and shear is not the right word for it.
Have you computed the lattice flux and lattice
No.
circulation
No.
for these modes?
No.
Because that's the criterion. If one of them is zero, then you can say, okay, that's the either tensile or shear mode. But if they're both non-zero, then
Maybe it's a matter of how we name them.
right.
That's the problem. But they have a symmetry property
Okay.
in there, so we can chat. I think. Yeah.
We've got time for a question.
Quick one.
A quick one. Yeah, so if you took your forcing as symmetric or anti-symmetric, then it would naturally uncouple into these two problems, and then you can add them together at the end. So it's not surprising your kernel ended up by being diagonal.
I think, yeah, absolutely. So I think we were just trying to solve this problem in generality and just blinded by the fact that we had this. But I agree.
Okay.
But change the chirality of your structure and then enforce your
Yeah, you could change a problem where you break that symmetry, and then you would couple it.
Something more interesting, yeah, for sure.
All right.
Okay, thank you.
Thanks again. I think we're to move on. Thanks.